This is part 2 of the notes on Taylor and Maclaurin polynomials. Last time we kind of covered the basics on how to form a Taylor polynomial. Today we're going to do a couple other things with Taylor polynomials, as well as start taking a look at some AP problems. This one asks us to write the first 4 non-zero terms of the Maclaurin polynomial for x squared times e to the x. If we try to do this like we did last class, and I wouldn't write this down here, but when we start taking derivatives, we're going to need at least 3 derivatives plus the function itself, although f of 0, my x value is 0 because it's Maclaurin. If I plug in 0, I get 0. So we're going to have to take at least 4 derivatives here. When I go to take the derivative, we have to use the product rule, which isn't bad. That's our first derivative. So our first derivative at 0 is still 0. To take the second derivative, I'm going to have to use the product rule here and the product rule here. And it can be done. Notice as I keep going, when I take the next derivative, I'm going to have to use the product rule multiple times. When that's the case, if I'm multiplying 2 things here, there's a better way to do these than having to use the product rule a whole bunch of times. So let's take a look at an alternative way of doing this. Last class we wrote down the Taylor polynomial for e to the x. You found it and then we verified it. If f of x is e to the x, all the derivatives, the first derivative, the second derivative, the third derivative, they're all e to the x. And if I plug in 0, I get 1. So all the derivatives at x equals 0 are equal to 1. So e to the x is 1 plus 1x plus 1x squared divided by 2 factorial plus 1x cubed divided by 3 factorial plus 1x to the 4th divided by 4 factorial, and so on. We need 4 non-zero terms, so this is e to the x. If we're just going to do x squared times e to the x, you can take the Taylor polynomial for e to the x and just multiply it by x squared. So I'm multiplying this whole thing by x squared. So we would just get x squared plus x cubed plus 1/2 x to the 4th plus 1 over 3 factorial x to the 5th. Which is significantly easier than having to use the product rule a whole bunch of times there. If this is something other than something that's polynomial, if it's like sine x times e to the x, the way you would do it is you would get the Taylor polynomial for e to the x, you would get the Taylor polynomial for sine x, and then you would start multiplying them together, and you would FOIL to however many terms that you need here. The second problem we need to look at, again, pretty common one that's on the AP exam. In this case, they gave us the Maclaurin series for cosine x. We actually, again, found it last class. And then it's going to ask us to use a certain number of terms, in this case, the first 2 terms of this series, to approximate cosine of 1/2. We want to find what cosine of 1/2 is approximately equal to. So we're just using the first 2 terms, so these 2 terms here, and notice my x value is 1/2. So cosine 1/2 would be equal to, or approximately equal to, 1 minus 1/2 squared over 2. These problems are almost always no calculator. So cosine 1/2 should be about 7/8. The approximation using just the first 2 terms is 7/8. And then part B wants us to show that our approximation has an error less than 1 over 150. Just like we did with power series, any alternating convergent series. So this one alternates, it goes back and forth. It is convergent. Notice all my terms are getting smaller and they're converging down to 0. So this is a convergent alternating series. If that's the case, the max error is always the next term after the one that we've used to make our approximation. So in this case, our max error is the next term, which for our problem is x to the 4th divided by 4 factorial. So our maximum area, or maximum error, is, remember my x value is 1/2. So 1/2 to the 4th over 4 factorial. 1/2 to the 4th is 1/16. 4 factorial would be 4 times 3 times 2 times 1, 24. 16 times 24. Is 384. So the maximum my error could possibly be is 1 over 384. 1 over 384 is the max error, which is indeed less than 1 over 150 because it has a bigger denominator. Like I said, these problems are almost always no calculator, so you wouldn't necessarily be able to check it on the calculator. But notice if you do type in cosine of 0.5 on your calculator, I don't know why my calculator is not pulling up there, but if you do type in cosine 0.5, make sure you're in radians mode, it gives us 0.87758. So cosine of 1/2 is 0.87758, which is awful close to 7/8. So this is the proper number. This is our approximation. If you subtract those two things, you'll find that they differ by 0.00258, which is a pretty small error there. It's very, very close to our max error of 1 over 384. All right, and then the last problem I want to do is an AP problem. This is, if you take a look at the assignment that is posted to Google Classroom, this is the first problem from that assignment. So it gives us, it says function f has a Taylor series about x equals 1. It converges to f of x for all x in the interval of convergence. They give us f of 1 and f prime of 1. And then it says the nth derivative is given by this formula. So this is a formula for the derivative of f at x equals 1 for any n values greater than or equal to 2. Part A wants us to write the first 4 non-zero terms and the general term for the Taylor series for f. So the Taylor series for f is the function value, so that's 1, plus 1/2 plus negative 1/2, so plus the derivative times x minus 1 to the first, plus the second derivative at 1, which we'll evaluate in a minute, divided by 2 factorial times x minus 1 squared, plus the third derivative at 1, divided by 3 factorial times x minus 1 cubed. So this negative 1/2 is because that's the derivative, the first derivative at 1, and this is the function value at 1. To get the second derivative and the third derivative, this is a formula for the nth derivative. So the second derivative, at 1 would be, we're going to plug 2 into the formula here. So if I plug in 2, I get a positive number. 2 minus 1 is 1 factorial over 2 to the second. And the third derivative at 1, if I plug in 3, I get negative 2 factorial over 2 to the third. So the first four non-zero terms of the Taylor polynomial are 1 minus 1/2 times x minus 1 plus 1/2 divided by 2, it's 1/4 times x minus 1 squared, plus the third derivative, which is negative 1/4. So I've got negative 1/4 divided by 3 factorial. 3 factorial is 6. That's going to be 1 over 24 times x minus 1 cubed. Now, there's a couple different ways you could find the general term. You could try to find the pattern, write it for this. I think pretty clearly we could maybe see that we're going to have an x minus 1 to the n here. It's to the first, to the second, to the third, and so on. We are going to have a negative 1 to the n. Notice I'm starting with n equals 0. So I do want to start with a positive term here when I plug in 0. And then try to figure out what the pattern here is between 2, 4, 24. Might take a little bit of work there to get. Another way you could do it is we know that this is going to be the nth derivative at 1 divided by n factorial. And then plug in our formula here. We already have the negative 1 to the n. That already took care of this part. So if I plug that in, I've got n minus 1 factorial divided by 2 to the n, and I've got n factorial on the bottom. The bigger one between these two is the n factorial. So if I start writing that out, I would have n times n minus 1 factorial. These cancel now. So our general term is I've got that negative 1 to the n times 1 over 2 to the n times n times x minus 1 to the n. Once you think you have it, then I'd start plugging things in here. Notice if we plug in 1, I get a negative value. I get 1/2. If I plug in 2, got x minus 1 squared. I've got a positive value. I've got 4 times 2. That's no good. My issue's way back here. Sorry, that's a mistake. When I plugged in 2 into the second derivative here, this should be 1/4. So that's 1/8, 1/4 divided by 2. My mistake. All right, so now it does check in the second one. Good thing we were checking. Now when I plug in 3, if I plug in 3, I get a negative value. I've got 2 cubed times 3 on the bottom. 8 times 3 does indeed give me 24. So our general term should look like that. The general term is like the nth one way out here. I do understand if you plug in 0 here, we are getting undefined because you divide by 0. That's not anything you need to worry about there. F of 1 is defined in the problem. Part B says the Taylor series for f about x equals 1 has a radius of convergence of 2. We are asked to find the interval of convergence and show our work. So we know we're centered at x equals 1. My radius of convergence is 2. So we're going to be going from negative 1 to 3. Add 2, subtract 2. And then the next thing we need to do is determine if it converges or diverges for each of these values. So we are going to check x equals negative 1, and we are going to check x equals 3, and we are checking those back into the general term for f of x. So if I plug in negative 1 into our general term here, if x is -1, way down here, we've got -1 to the n times -1 minus 1 to the n divided by 2 to the n times n. And if I'm plugging in 3, it would look like this. X equals 3 is a little bit easier, so let's start over on that one. Here I've got 2 to the n divided by 2 to the n cancels. -1 to the n over n. It's an alternating series. It alternates the limit as n approaches infinity of 1 over n is indeed 0. And my terms decrease. 1 over n plus 1 is always going to be less than 1 over n. The next term is always less than or equal to the previous term, as long as n is greater than or equal to 1. So my terms are decreasing. Therefore, this alternating series decreases. Or decreases, converges. So at x equals 3, we have a convergent series. This is -2 to the n. -2 to the n times -1 to the n. We can multiply the bases. That is 2 to the n divided by this 2 to the n. Those cancel. So this one simplifies to 1 over n. 1 over n diverges because it is a piece series, where p is less than or equal to 1. So diverges when x is -1. Part C. Part C says the Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So here's our alternating series that it was asking for. So we've got 1 minus 1/2 times x minus 1 plus 1/8, not 1/4, 1/8 times x minus 1 squared. It wants the first 3 terms, first 3 non-zero terms, and our x value is 1.2. 1.2 minus 1. It might be easiest, especially since I'm squaring this and then times 1/8 without a calculator, to change this to 1/5. So I've got 1 minus 1/10 plus, this is 1 over 25 times 8 over 200. Times 20 for my common denominator, times 200 for my common denominator, 181 over 200. So that's just a matter of plugging 1.2 into your first 3 terms of your Taylor series. And then part D, show that the approximation found in part C is within 0.001 of the exact value of f of 1.2. So what we are looking for is we want to show that the error, how far it's off by, is less than 0.001. We want the error to be less than 0.001. So the maximum error would be if I plug in 1.2 to the next term. So I use 3 terms to approximate. If we plug in 1.2 right here, so 1 over 24 times 1.2 minus 1 cubed. 0.2, which is 1/5 cubed. So we have 1 over 24 times 1 over 125. You could multiply out 24 times 125 without a calculator if you had to. It's 3,000. So the max error is 1 over 3,000, which is indeed less than 1 over 1,000, which is 0.001. So that is Taylor series. A lot of these AP problems, they're all kind of a little bit different. Like in this one, when they gave us a formula for the derivative, sometimes they ask directly for the Taylor series. Often it'll ask for an interval of convergence. Often there will be one of these error type problems, but not always. We'll spend the next few classes practicing these, going over them, that sort of thing.